It's a chain rule when you have multiple variable system or function of multiple variables, pretty much the same as the chain rule that you learn in Calculus 1. There are basically three cases, and the third one is a general case. So I'll start with the simple case where we have a function of z equal f of x and y, which is a surface. Okay, and let's say that this function is differentiable with respect to x and y. X and y themselves are function of t, such that, let's say, x is a function g of t, and y is a function h of t, and both g and h are differentiable on some domain of t. And now we want to express a z, the derivative of z, not in terms of its partial derivative, del z del x and del z del y, but we want to express it as the derivative of with respect to t. In other words, we are after dz dt. Okay? Notice that I dropped the del notation because you have only single variable t. And that's case 1. So it's dz dt, it's a complete derivative. So let's write the supposition here. Okay? So the supposition that you have z equals f of x and y is differentiable with respect to x and y on some domain D, okay, and x is a function of t, y is a function of another function of t, are both differentiable with respect to t on their domain. Or domains, because each one may have a different domain. So we're going to say that in this case, then z is differentiable with respect to t and its derivative now we'll call this, since again I said it's a single variable derivative, so dz dt is given by the chain rule. So here's the chain rule. We're going to write dz dt
at the bottom left.
Bottom with respect to t, yeah, thank you. Let me space because it's hard enough to realize that WRT is with respect to, unless you heard me saying it gazillion times before. Okay, so dz dt, we're going to express it as del z del x dx dt plus del z del y dy dt. Now notice that I did not use partial derivative notations for dx dt and dy dt, as well as dz dt, again because those are functions of single variable, so they are complete derivatives. So quick example, let z equal x squared y plus 3xy to the fourth, and let's x equal sine of 2t, y equal 2 cosine, no, y equal cosine t, like so. And we want to find dz dt when t equals 0. All right, so I'm looking on top here, and I see that I need to have 4 players in place to compute this. So I need first the partial derivative del z del x and del z del y. So del z del x and del z del y are the following. I'm looking at this function, so it will be 2xy plus 3y to the fourth, right? Then next to it, I need also dx dt, so I'll take dx dt at this time, and x is sine 2t, so dx dt is 2 cosine 2t. And del z del y, looking back on top, is x squared plus 3 times 4, so that will be 12xy cubed. And also in dy dt, and that's simply going to be negative sine t. Now, I need to evaluate stuff at t equals 0. So at t equals 0, I need to evaluate x and y, and therefore del z del x and del z del y. So what is x at t equals 0? Well, at t equals 0, x equals 0, and therefore and y equals 1, right? What about dx dt? Well, dx dt equals 2, and what about dy dt? It's 0. So what's left to evaluate is del z del x and del z del y. Okay, so del z del x when t equals 0 equal, if x equal 0, so we have 0 plus 3y, so it's simply 3. And del z del y when t equals 0, I'm looking here, x equals 0, and so it's 0. So dz dt when t equals 0 becomes del z del x is 3 times dx dt, which is 2, plus del z del y, which is 0, times dy dt. This is just. So we end up having 6. So this wasn't too painful, wasn't it? It's pretty straightforward.